Good morning, Adriana. This is a doozy. Let's see if we can do this. You have a half circle of charge running from here to here. The total charge is 3 microcoulombs. The radius is 5 centimeters. It wants to know something about an electron passing through the center of the ring. What's the acceleration of the electron? But you want to know what's the electric field um, at the middle here. And so first, let's say the electric field is the integral of dE. And then let's say you have some charge here. This is your r hat vector. This is your angle in this problem, phi. These are vertical angles. That's the same angle. The components would say this is dE x and this is dE y. And trig says that this is dEx is equal to dE times cosine phi, and dEy is dE sine phi, but it's going in the negative direction. So let's just put a negative sign in front of that. Now, let's just skip ahead and say, like, if you do the integral of dEx, all the left stuff cancels all the right stuff, and this will actually equal 0. So if we do a little x here, we said this would be 0 by symmetry. So let's go after the y component. So this is the integral of dE y, which is integral of negative dE, if I could spell sine phi. So our next task is this guy. What is dE? Well, E is kq over r squared. So dE is k dq over r squared. Okay, we're making some progress. This is the integral of negative k dq over r squared times sine of phi. Now we have to go over dq. We have to try to figure out what dq is. And this is a little weird, but we use this letter lambda to be charge per length. This is linear charge density. So this would be, let's say, q over arc length s. Let's make it dq over ds. Multiplied, well, let me think for a second. So yeah, let's multiply over. So we say lambda ds equals dq, and then realize that ds, I know this is getting into the weeds here, but arc length equals r times theta, so ds equals r times d theta, or phi, whatever you want to say. So now lambda r d phi, just make this a phi to match our earlier angle, equals dq. All right, this is progress. We're getting somewhere. So now we'd say that electric field y is integral negative k dq over r squared sine of phi, which is integral negative k. Now we're going to replace dq. dq is lambda r d phi. We still have sine phi over r squared. So let's cancel the r. Rewrite it in a normal order. something like this. Now, what are we integrating? D feet. So in our problem, we go from here to here. So our limits are 0 to pi. And we're going to pull constants to the front. So negative k lambda over r, integral from 0 to pi of sine phi d phi. This is our electric field in the y direction. So we're so close. We're so close. So we integrate sine of phi, and we get, what do we get? We get negative cosine phi. We evaluate from 0 to pi. So let's just plug this in. Pi, cosine of pi. All right, so this is pi, and this is negative 1 comma 0. So this is negative 1, so it's negative negative 1, so it's positive 1 minus, if I plug in 0, cosine of 0 is 1, so minus 1, so plus 1. So it's negative 2k lambda over r, and that's what electric field is in the y direction. Now, we plug in, we go back, remember that lambda is charge per length. This is going to be negative 2k. Lambda here is going to be q divided by pi r over r. Why pi r? Pi r is the length of half a circle. 2 pi r divided by 2, or pi r is the arc length. And plug in these numbers, and I think you get the answer you're supposed to get. I think you get, what is it, 6.8. Well, when I did it, here's what I got. I got negative 6.8659 times 10 to the 6 newtons per coulomb. And technically that's k hat. So that's the electric field in the y direction.